Okay, good morning. Today we'll discuss growth rate of functions because it's related to next thing we're going to discuss, solving recurrence relations in connection with divide and conquer algorithms, which is very important in computer science. All right. So typically, when we measure learning time of an algorithm, we express it as a function of input size, so which is normally a function from natural number to positive real numbers. So when we measure learning time of an algorithm. But in computer science, very often, the actual function is not very important. Rather, it's the symptomatic behavior, such as when n is relatively large, how fast the function grows, because give us a guideline of fast the algorithm runs in practice. So typically, instead of a very complicated function like this one, it's very hard to understand what's going on. It will be much easier to use a much simple notion called the big O notation or asymptotic notation to denote the behavior of the function when n is large. It's much easier to understand this function n cubic than this function. And actually, for us, when we implement an algorithm, of course, the actual learning time is important, but the learning time actually is affected by a lot of things. These constants do not really mean a lot because it depends on speed of algorithm, your algorithm, the speed of your computer, your compiler, many other things. So these constants are not that important. Rather, the how fast the function grows plays a much more important role. So therefore, instead of the actual function, we much better to see how fast the function grows in terms of very simple function. So that's the idea behind growth rate of functions. So instead of this complicated function f, what we would like to know is what's an upper bound of this function when n is large. But here we try to bound this function by a very simple function, c a constant time function, so that whenever this function is large enough means it's large enough. When n is at least this number, then this function always below the blue one, always below the red line, a red curve. Okay, so that's the idea behind the big O notation or asymptotic notation. Mathematically speaking, we say that a function f of n is bounded above by another function g of n, asymptotically bounded by g of n. In notation, we said fn equals big O of gn. And sometimes you can also see that we use this notation. So sometimes you will see we use this notation. We want to order them, all the functions, then we may use this notation. It's a very loose analog when we use when we compare numbers, say x at most x squared, things like this. It's analog to this one, but very loose. Okay. So mathematically speaking, when we say that a function is big O of gn, that means there exists two constants. Both of them are positive numbers. N naught is here, and C is here. So there are two constants, one here, one here. Okay. Such that whenever n is large enough, so when n is surpass n naught, then this function is always bounded above by g of n. So that's the meaning of big O notation. All right. So the idea is just it's the simplification. We use a simple function to approximate the behavior of a complicated function f of n when n is large enough, because that will be sufficient. For computer science, it will be sufficient to use use gn as a guideline of how fast algorithm runs. Okay. So for example, this complicated function can be bounded above the n cubic. So we can just say this one is big O of n cubic. So this gives us a guideline. Suppose our algorithm runs in this much time. So typically we use T of n as running time of our algorithm. Then instead of looking into this complicated functions, we can just use say the Tn is order of n cubic. So that gives us a rough estimate how our algorithm runs in terms of space of input. All right. So one good thing about computer science is usually we can be lazy. Instead of give all these details, there are no need. Instead, we can just say n cubic. So that's very good. And in practice, actually, that's very useful because this actual function is not that useful in practice as a guideline to the running time of algorithm. Instead, rather this one, because typically we deal with large n. If n is small, then we don't need to bother about these things at all. You can always try our possibility if n is small. If n equals say 7, it's very small. So you can try our possibility even to the power 7. It's very small. 1 to 8, right? So we don't bother. The problem is when n is large. So the idea is to see how fast it grows. Okay, so let's take our notation. So the basic notation is big O notation. All right. Now from big O notation, there are two more notations. Big omega and big theta. So what does that mean? That means this one means lower bound. This one means upper bound. So whenever Fn is big O of G of n, then we say that Gn is omega of Fn. So that one still at the lower bound. And this one means tight bound. So this one's the upper bound. Theta means theta means Gn is both an upper and lower bound of Fn. So it's a tight bound. Basic notation is this one. Once we have this one, these two follows immediately. All right. So let me draw a picture of this one, what this one means. Typically, you see these two. Most of you will not see this one at all, I think. Very few of you will have to meet with this one. Many of you will deal with big O and big theta. All right. Now, this one theta means the function f of n is lying within this band, defined by C2Gn, C1Gn, C1, C2 constant. So whenever n is large enough, then the function is within this band. So here does not matter, can be anything. So that kind on the means. All right. So that's very closely describe the behavior of function f of n in terms of its growth rate when n is large enough. All right. Okay, so that's the basic idea. Let me just give you one simple example. One simple example to illustrate it. Let's see, say. All right, suppose fn equal n squared plus 100n. So I want to show that fn is bounded above by n squared. So we can ignore this part in terms of its growth rate. So by definition, what we need to show is exists C and N naught such that that's what we need to show by definition. So we need to find these two constants, C and N naught. All right. Okay, in this case, actually, because this was very simple, it's very easy to see. If I set, say, C to be 2, let's see. Okay, let's try two different ways. Okay, C can be set to be different. If I set C to be a particular number, then N naught will depend on C. So here, easiest way is to set maybe C equal to 100. Okay. Actually, I not needed to that big. Maybe 101 will be good enough. 101 maybe. It's easy. 101. Okay. Now, if I set C to be 101, what we have is n squared plus 100n less than equal n squared plus 100 n squared. When n at least 1, right? So here I can take n naught to be 1. This one. So from here, what we get is 101 n squared. So which is c n squared. Typically, when we can fix the c, then we'll get a proper number n naught. Now, if you accept c to be a different number, okay, say c equals say 2 maybe. I don't know when it works. Sometimes the particular c may not work. Okay, if I set c to be 2, then I need to find another n naught such that n squared plus 100 and less than 2 n squared. We want to find this n. To satisfy this one. Okay, something happened. Your meeting will end in 10 minutes. Something strange. I don't know whether it will be interrupted. Suddenly I get a message saying my meeting will end in 10 minutes. Something wrong with that Zoom, maybe. I will see. Okay, once it stops, maybe I log in again. I don't know what's going on. I just got a message saying meeting will end in 10 minutes from Zoom. Okay, so in case there are interruption in 10 minutes, I'll try to re-log in. I don't know what's going to happen in 10 minutes. Okay. Someone sent me something. Let's see. I don't know what this. Okay, now, so if I set C to be 2, I need to find an n naught for n to satisfy this one. So in this case, we have n 100. So then n naught will be 100. So typically this pair depends on each other. So when I choose, so here I have a pair, Cn pair, Cn naught pair. Here is 101 and 1. Here is 2 and 100. All right. And usually it's very easy to prove it, but that's kind of tedious because we need some algebra in order to make it work. For this, as far as this code concerned, I don't think there's a need to do such things. I say basically no need. Rather, I will give you some basic orderings, then you can use basic ordering to obtain bigger notation for a complicated function. Okay, but this one give you an idea. How can we prove that indeed a function is upper bounded by another function? So basically, we need to find these two numbers. Usually, we can use induction, for example, or direct manipulation. All right. Okay. Now let's see. Let me give you some important ordering first. For 99% of you, and or 99% of us, we only need three types of functions. One is a logarithmic function of or its powers, and the polynomial function and exponential function. We only need three types of functions. One is logarithmic function. This logarithmic function. One is polynomial function. Another one is exponential function. All right. So of course, this base is at least one. So here C is positive. And here the base A again is at least one. So if you remember from in high school, the behavior of these three functions. A logarithmic function grows very slowly. It's logarithmic function. Polynomial function grows fast. Maybe something like this. Exponential function grows extremely fast. So that's AN and C and log EN. So in terms of their growth rate, we always have the following. So regardless of how small this C is, logarithmic function always smaller than this one. And regardless how small this one is, any polynomial function grows slower than exponential function, regardless of how small this A is. For example, we can have 1.001 to power n. Here, and C can be huge, maybe n to 1. All right, even for such a it's a polynomial function, we always have this one is bounded about by this one. So for actually for this one in practice, even for large n, this one is bigger than this one. But when n tends to infinity, when n is large enough, this exponential function always surpasses a polynomial function. Okay, now in connection with daily life, what does this one mean? In connection with daily life, what does this one remind you? This one is 1 plus r to power n. So this r, if you interpret it as interest rate or inflation, so this one is very small, but as time goes by, this number will grow very, very fast. So eventually, as years goes by, you need to pay back a lot. As year goes by, the money you have nowadays, after many years, it's worth nothing. If you look at inflation, after many years, it just means nothing. All right. Okay. So that's the very most important ordering as far as we are concerned. Logarithmic function is always bounded above by polynomial function, which is always bounded above by the exponential function. Let's see whether it stopped or not. No, it's still working, I think. No, I did not set time limit. Yeah, I have no idea what's going on, but it's still okay now for the time being at least. Okay, it's still haven't stopped, I think. Okay, now use this basic things and with some property of big O notation, we can basically will be able to determine ordering of any functions for us. I mean, any function you account 99%. All right. So there are some very basic important, very important properties of big O notation. Suppose we have F1n is big O of G1n and F2n. So we have two different functions. Now we look at combination of these two different functions. The first one is of course addition. Addition, summation of two functions. Then in some big O notation, that's is summation of their upbound, which is actually that's very useful. It's the maximum of these two. Okay, how can we use this one? This one is very useful. For example, for this function, all right, we can use this property to say that this one is big O of this one. Typically, this one is called the leading term. The leading term. For function, it's a summation of other functions. One that grows fastest is called the leading term. So among these functions, this one grows the fastest.